One more of these exercises with a similar setup where our plane region is defined by the area between this line here and the parabola, and there's our representative rectangle. But this time, our cross sections made perpendicular to the x-axis are going to be equilateral triangular cross sections. Here, let's draw an image of that thing. If I want to find the volume of the resulting three-dimensional shape, I need to find the volume of one of these and then add them all up with a definite integral. So what shape is that? Obviously, this thing is a triangular prism. To find the volume of a triangular prism, it's the area of the base multiplied times the height. The base for us, of course, is the triangular cross-section, the equilateral triangle that's right there. And then our height is going to be the width of our partition, the delta x. So then, let's compare some lengths in this diagram with ones in the original picture here. So the good old-fashioned top minus bottom, the g of x minus f of x, that's the base length of our isosceles. And by isosceles, I mean equilateral triangle. It is isosceles technically. Anyway, so the height of it, though, is not g of x minus f of x. That would only be true if this was a square. So instead, remember from the warm-up activity, we drew in our height thusly, and it made a 30, 60, 90 right triangle over here. And the bottom part, the small leg here, is half of that g of x minus f of x. And then if I multiply that times the square root of 3, I'm going to get the height of our equilateral triangle. So we have the square root of 3 over 2 times g of x minus f of x. All right, and then once again, our width of our subinterval is just a dx. Let's put these pieces together in order to find the volume of this shape, and we'll take a look at it one more time. So, boop, there we go. Our area function is going to be the square root of 3 over 4 times the side length. Do you remember coming up with that in one of those 1001 warm-up videos? Yeah, of course, right? So here's our side length, which we're going to square, and then we're going to multiply it times the square root of 3 over 4, right? So it's basically base times height, and then we multiply that by half, which is where that 4 down there in the denominator comes from. Okay, so let's write up our definite integral. Still exactly the same bounds from -1 to 2, and then our area, square root of 3 over 4, multiplied times our side length. Our side length is that, not f of x, come on, g of x top minus f of x bottom, which is squared with respect to x. And then I can take the square root of 3 over 4 out of this thing, just like that. How nice is that? And then maybe scooch this thing over. And then let's say I wanted to compare that to the square and the semicircle. The only difference here is the scalar that's right out in front of the square root of 3 over 4, which is making it an equilateral triangle's volume instead of, let's say, pi over 8, which is making it the semicircle, and then the 1, which is making it a square. Here, let's take a look one more time at a model for this. Bear with me as I call up the camera app. Ta-da! All right, so you can see our equilateral triangular faces where the base length is basically the distance between the 2 points, corresponding points on our functions. Ta-da!